Right now, as you lie here, something is passing through you. It moves through the roof. It moves through the ceiling, through the air above your bed, through the blanket, through your skin, through the bones of your ribs and the chambers of your heart, and out through the mattress and the floor and the ground beneath the house. It is moving at hundreds of kilometers per second. It does not slow down. It does not scatter. It leaves nothing behind, no heat, no mark, no trace of any kind. Billions of particles every second. For every second you have been alive. Roughly 85% of all the matter in the universe is made of this. We can map where it is. We can weigh it. We can watch it bend light around galaxy clusters and calculate its mass to within a few percent. And after 90 years of looking, we cannot say what it is. Every star you have ever seen, every planet, every galaxy, in every photograph ever taken, all of it is the exception. It is the thin, luminous residue on top of something far larger that does not shine, does not reflect, does not absorb, does not warm, does not glow. Something that built the scaffolding every galaxy grew inside. Something that went first and made everything else possible, and then stayed dark. And it is in the room with you, right now. Hello, and welcome to Sidereal. Tonight we are going to spend some time with the invisible universe, the dark matter that fills the space between the stars, the ordinary matter that makes up the small bright fraction we can see, the black holes that swallow light entirely, the force that is pushing the galaxies apart, and the oldest light in existence, which is passing through this room as well. If you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps. And I am curious where you are listening from. Drop your location and the time in the comments. It becomes a kind of map, night after night, of people lying awake under the same sky. Here is the question we are going to sit with. We can weigh the invisible. We can map it. We can prove that it is there. Why, after 90 years, can we still not say what it is made of? Now, let us begin. 1. The sea in the room. Start with the simplest possible statement of the problem. Add up everything in the universe, all the energy, all the mass, everything that has any weight at all. Ordinary matter, the kind of matter you are made of, the kind that forms stars and planets and gas clouds and dust and human bodies, accounts for about 5% of that total. Dark matter accounts for about 27%. The remaining 68% is dark energy, which we will come to much later tonight, and which is a different problem entirely. If you set the dark energy aside and look only at the matter, only at the things with mass, the things that clump and fall and pull on each other, then the ratio is starker. About 85% of the matter in the universe is dark. 15% is ordinary. For every kilogram of everything you have ever touched, there are more than 5 kilograms of something else. It is not dark in the way a storm cloud is dark. A cloud is dark because it blocks light. It absorbs some, scatters the rest, and casts a shadow. Dark matter does none of this. It is transparent, not translucent, not faintly hazy, transparent in a way that nothing in ordinary experience is transparent. Light passes through it as though it were not there, because as far as the light is concerned, it is not there. Radio waves cross it, microwaves cross it, infrared, visible light, ultraviolet, X-rays, gamma rays, the entire electromagnetic spectrum, from the longest wavelengths to the shortest, passes through dark matter without the slightest interaction. It does not emit. It does not absorb. It does not reflect. It does not scatter. The only thing it does is pull. That is the whole of our contact with it. Gravity. It has mass, and mass curves space, and things fall toward it. Every single thing we know about dark matter, we know because something that we can see moved differently than it should have. Consider what that means as a piece of scientific evidence. If you could switch off all the dark matter in the universe tomorrow, the light would not change. Not a photon of it. The stars would look identical. The nebulae, the galaxies, the sky above your house all the same. And then, slowly, over hundreds of millions of years, everything would come apart. The galaxies would unwind. The clusters would disperse. But the visible universe, the one we can photograph, would look for a long time exactly as it looks now. The thing that holds it together is not the thing we can see. Here is what it is doing in your room. The local density of dark matter in this part of the Milky Way, in the neighborhood of the Sun, is about 1/3 of a proton mass per cubic centimeter. That is the number astronomers arrive at when they model the mass of the galaxy against the motions of nearby stars. Written out, it sounds like almost nothing, 1/3 of the mass of a single proton in a volume the size of a sugar cube. But it depends entirely on what the particle is. If dark matter is made of heavy particles, then there are very few of them, and they are widely spaced. If it is made of light ones, there are more. And one of the two leading candidates, a hypothetical particle called the axion, is extremely light, so light that if dark matter is made of axions, then something like 10 trillion of them are inside your body at this moment, and roughly 100 billion pass through the area of your thumbnail every second. They do not collide with the atoms of your skin. They do not disturb the electrical signals moving down your nerves. They do not deposit energy. They fall through you the way light falls through an open window, and then they are through the mattress, and through the foundations, and through the crust of the earth, and through the mantle, and through the iron core, and out the other side of the planet, and back into space, having noticed nothing. The earth does not stop them. The earth is not, as far as they are concerned, in the way. And they are not drifting. They are moving. The solar system is orbiting the center of the galaxy at about 220 kilometers per second, and the dark matter halo, which is roughly spherical and does not rotate with the disk, is effectively standing still around us, which means we are plowing through it. The Sun is moving through a stationary sea at a couple of 100 kilometers per second in the direction of the constellation Cygnus, and has been doing so for 4.5 billion years. Physicists call this the dark matter wind. It has a direction. It comes from Cygnus. And because the Earth also orbits the Sun, our speed through that wind changes over the year slightly faster in June, when Earth's orbital motion adds to the Sun's, slightly slower in December when it subtracts. The difference is small, about 7%, but it is a real, predictable, annual signal. If you had a detector sensitive enough, you would see it breathe once a year. That prediction is the reason a great deal of expensive equipment has been buried underground. Deep beneath the Apennine Mountains of central Italy, under 1,400 meters of limestone, there is a laboratory called Gran Sasso. It sits in a cavern beside a motorway tunnel, and it exists because rock is very good at stopping cosmic rays. At the surface of the Earth, several hundred cosmic ray particles pass through your body every second, and every one of them would swamp a dark matter detector. Under 1.5 kilometers of mountain, that flux drops by a factor of about 1 million. Inside that cavern sits a tank of liquid xenon. Xenon is a noble gas. It does not react with anything, which makes it clean, and when it is chilled to about 100 degrees below 0 Celsius, it becomes a dense, clear liquid, heavy with large nuclei that make a big target. The tank is surrounded by photomultiplier tubes, light detectors so sensitive that a single photon registers, and the entire apparatus is designed around one hoped-for event. A dark matter particle strikes the nucleus of a xenon atom, knocks it sideways, and that recoiling nucleus produces a tiny flash of light and a small cloud of freed electrons. Two signals, microseconds apart, from one collision that has never been seen. The experiment is called XENON. It has been running, in successively larger versions, for more than 15 years. It has recorded nothing. The same emptiness is being recorded elsewhere. In an abandoned gold mine in South Dakota, a mile below the surface, in a chamber that once held the miner's machinery, there is a detector called LZ, another xenon tank, larger than the Italian one, currently the most sensitive dark matter detector ever built. It has recorded nothing. Under a marble mountain in Sichuan province, in the deepest underground laboratory in the world beneath more than 2 kilometers of rock, a Chinese experiment called Pandax runs the same search with the same technology. Nothing. In a salt mine beneath Lake Huron, in a tunnel under the Pyrenees, in a mine in Canada. Nothing, nothing, nothing. Meanwhile, in a laboratory at the University of Washington, a different kind of instrument is hunting a different particle. If dark matter is made of axions rather than heavy particles, it will not knock nuclei around at all. Instead, inside a strong magnetic field, an axion should very occasionally convert into a photon, a single microwave photon, at a frequency set by the axion's mass. which nobody knows. So the experiment, called the Axion Dark Matter Experiment, is essentially a radio. A supercooled copper cavity sits inside a powerful magnet, and it is tuned, slowly, frequency by frequency, listening for a signal that would arrive as a faint excess of microwave power at one particular channel and nowhere else. It has been scanning for years. It has covered a small fraction of the possible frequencies. It has heard nothing. There is one exception, and it is worth naming honestly, because it is the only crack in an otherwise uniform silence. An experiment at Gran Sasso called DAMA, using crystals of sodium iodide rather than liquid xenon, has reported for more than 2 decades that its signal rate rises and falls over the course of the year, peaking in early June, troughing in December, exactly as the dark matter wind predicts. The statistical significance of that annual modulation is enormous. If it is real, it is a detection, but no other experiment has ever reproduced it. Detectors that are more sensitive by orders of magnitude, searching the same parameter space, see nothing at all, and if DAMA's signal were dark matter, they should have drowned in it. A replication experiment in South Korea, built specifically with the same sodium iodide crystals to test the claim directly, has not confirmed it. Most physicists now believe the modulation is real, but its cause is terrestrial, something about the environment of the detector that also varies with the seasons. Nobody has proved what. It sits there, unexplained and unaccepted, a result that almost everyone believes is wrong and nobody can quite kill. That is the state of the direct search. 90 years since the first hint, 40 years since the serious hunting began, and the honest inventory is no detection, one disputed anomaly that nobody trusts, and a set of exclusion limits that grow tighter every year. Those exclusion limits matter more than they sound. A null result is not nothing. Every year a detector runs without seeing anything. It rules out a slice of possibility. It says, whatever dark matter is, it does not interact with ordinary matter this strongly. And slice by slice, the space where a heavy particle could be hiding has been shrinking. 20 years ago, the favoured candidate, the weakly interacting massive particle, sat in a comfortable range of masses and interaction strengths that theory found natural, and that the detectors were expected to reach. The detectors reached it. The particle was not there. The theorists moved the goalposts, and the experimentalists built bigger tanks, and the particle was not there either. And there is now a flaw beneath the search. Neutrinos, real, ordinary, confirmed neutrinos, streaming from the sun and from the atmosphere and from ancient supernovae, interact so weakly with matter that they too are almost invisible. But almost is not entirely. As the xenon detectors grow more sensitive, they are beginning to approach the point where they will start detecting neutrinos constantly as an irreducible background hum. Physicists call it the neutrino fog. Below it, distinguishing a dark matter signal from the neutrino noise becomes very hard. We are running out of room to look in this particular direction. The tanks under the mountains are only one of 3 ways to hunt. The second is to look for dark matter destroying itself. If the particle is its own antiparticle, which many of the candidate theories require, then wherever the density is high enough, 2 of them will occasionally meet and annihilate, converting their mass into a burst of ordinary particles, gamma rays, positrons, antiprotons, things we can detect. So astronomers point gamma-ray telescopes at the places where the dark matter should be thickest, the centre of the Milky Way, where the halo is densest, and the small satellite galaxies orbiting us, which are almost entirely dark matter and almost entirely free of the ordinary astrophysical sources that would confuse the signal. There is an excess of gamma rays coming from the centre of the galaxy. It has been there in the data for more than a decade. Its energy spectrum is, embarrassingly, about what you would expect from annihilating dark matter of a plausible mass. It is also about what you would expect from a large population of millisecond pulsars rapidly spinning neutron stars, which produce gamma rays and which ought to be concentrated in the galactic centre, and which are too faint individually to be picked out at that distance. The debate over which explanation is correct has run for years and is not settled. The signal is real. Its cause is not agreed. The satellite galaxies, which should show the same excess if it is dark matter, show nothing. There is also an anomaly in the antimatter. A detector mounted on the outside of the International Space Station has been counting cosmic ray particles for over a decade, and it finds more positrons at high energies than the standard astrophysical sources should produce. It could be dark matter annihilating, it could also be nearby pulsars. It is once again a signal that is real, and an interpretation that is not. The third approach is to make the particle rather than find it. In the Large Hadron Collider, protons are driven into each other at enormous energies, and if dark matter particles exist at an accessible mass, some collisions should produce them. They would leave no track, they would fly through the detector without touching it, exactly as they fly through the Earth. But the collision must conserve momentum, and so their departure would show up as an imbalance in the debris, a spray of ordinary particles all leaning to one side, and nothing at all on the other. Physicists call the signature missing energy. The collider has been running, in various configurations, since 2010. It found the Higgs boson. It has not found missing energy that cannot be accounted for by neutrinos. 3 methods: detect it arriving, detect it destroying itself, manufacture it. All 3 have been running for well over a decade. 2 ambiguous excesses that most physicists attribute to pulsars, 1 disputed annual modulation that nobody can reproduce, and otherwise nothing. Some of the candidates have already been killed outright. For a while, one of the most reasonable proposals was that dark matter was simply ordinary matter that happened not to shine dead stars, cold planets, failed stars, black holes, rogue bodies drifting between the stars in enormous numbers. They were given a name that was a deliberate joke aimed at the rival theory: MACOs, massive compact halo objects. They were testable. If the halo of the Milky Way were full of dark, dense objects, then occasionally one of them would drift precisely in front of a distant star, and its gravity would act as a lens, and the star would briefly brighten and then fade in a very particular symmetrical, colourless way. So 2 collaborations spent years monitoring millions of stars in the Large Magellanic Cloud, watching for those brightenings. They found some. They did not find nearly enough. The microlensing surveys established that compact dark objects can account for only a small fraction of the halo mass. Whatever the dark matter is, it is not dead stars. It is not cold planets. It is not, in any meaningful quantity, black holes of stellar size, which leaves us where we are. It is not ordinary matter in a dark form. It is not something we have found in a collider. It is not something that has ever announced itself in a tank of xenon a mile underground. And yet we know, with a confidence that comes from 4 completely independent lines of evidence, that it is there. The first of those lines was drawn by a man who was, by universal agreement, almost impossible to work with. 2 Zwicky, and the cluster that should not exist. Fritz Zwicky called his colleagues spherical bastards. Bastards, he explained, because whichever way you looked at them, they were bastards. He said this in print. He said it about people he worked beside for 30 years. He was born in Bulgaria to Swiss parents, trained in Zurich, and spent almost his entire career at the California Institute of Technology, where he was disliked with a consistency that is itself a kind of achievement. He was aggressive, contemptuous, physically imposing, and convinced often correctly, which made it worse that he was right and everyone else was slow. He carried grudges for decades. He was also, by any reasonable accounting, one of the most productive imaginations in 20th century astronomy, and he was ignored for most of his life. In 1933, 3 years into his time at Caltech, he turned his attention to a swarm of galaxies in the constellation Coma Berenices. The Coma cluster is one of the richest galaxy clusters in the nearby universe. It sits about 320 million light-years away, and it contains more than 1,000 large galaxies, bound together, orbiting a common centre of mass. From Earth, it is a faint scattering of smudges in a small patch of northern sky. In reality, it is one of the largest gravitationally bound structures we know of. Zwicky wanted to weigh it. The method he chose was old and sound. It is called the virial theorem, and it comes out of classical mechanics. For any system of objects held together by their own gravity, a star cluster, a galaxy, a swarm of galaxies, there is a fixed relationship between how fast the objects are moving and how much mass is holding them in. Fast motions require a deep gravitational well. A deep well requires a lot of mass. If you can measure the speeds, you can infer the mass without ever needing to see what is producing the gravity. So Zwicky went to the Mount Wilson Observatory, above Los Angeles, and measured the speeds. He took spectra of individual galaxies in the cluster and read their Doppler shifts, how far their light was displaced toward the red or the blue by their motion toward or away from us. He was not measuring one velocity, he was measuring the spread of velocities, the scatter, the degree to which the galaxies were flying around inside the cluster, rather than sitting still. The scatter was enormous. The galaxies were moving, relative to each other, at something like 1,000 kilometers per second. He then estimated the visible mass of the cluster the obvious way. Count the galaxies, estimate the mass of each from its brightness, add them up. The two numbers did not agree. They did not disagree slightly. Zwicky calculated that to hold the coma cluster together at those velocities, there would need to be roughly 400 times more mass than the visible galaxies could supply. Without it, the cluster was not a cluster at all. It was an explosion in progress, a swarm of galaxies moving far too fast to be bound, which should have flown apart and dispersed long ago, and which would not have survived to be observed by anyone. But there it was, intact. 900 million years of light, arriving at Mount Wilson from an object that ought not to exist. His conclusion was that the missing mass was there and simply could not be seen. He wrote the paper in German for a Swiss journal, and he gave the missing substance a name, Dunkel Materia, dark matter. The name has survived for 90 years. Almost nothing else about the paper was accepted at the time. It is tempting to tell this as a story of a genius ignored by fools, and it is partly that, but only partly. The truth is more interesting and less flattering to Zwicky, and more flattering to the caution of his colleagues. His number was wrong, badly wrong. The factor of 400 is not the factor we would quote today. The modern figure for the missing mass in a cluster, like coma, is closer to 5 or 6. The reason is that Zwicky's calculation depended on knowing how far away the cluster was, and in 1933 nobody knew that. The distance scale of the universe rested on Edwin Hubble's measurements, and Hubble's calibration was off. The constant he had derived implied a universe expanding far faster, and therefore a universe far smaller and far younger than the one we now measure. The error was a factor of about 7. Everything downstream of it, including Zwicky's mass estimate, inherited that error and amplified it. So when other astronomers looked at a result claiming that the universe was mostly invisible, based on a distance nobody trusted and a technique applied to a system nobody was sure was even in equilibrium, they did what careful people do. They waited. And there was another reason to wait. The virial theorem only works if the system is settled, if the galaxies have been orbiting long enough to have reached a stable statistical state. If the coma cluster was still forming, still collapsing, still assembling out of infalling material, then it would not be in equilibrium, and the theorem would give a meaningless answer. In 1933, nobody could rule that out. Clusters were new objects. Their dynamics were not understood. Zwicky's assumption might simply have been inapplicable. He was not entirely alone. 3 years later, an American astronomer named Sinclair Smith measured the Virgo cluster, the nearer and looser swarm of galaxies that our own local group is falling toward, and found the same discrepancy. The galaxies were moving too fast for the visible mass. Smith was cautious about it. He suggested the missing mass might be in some form of internebular material gas, dust, something ordinary but unseen. He died 2 years later, aged 38. And a year before Zwicky, in the Netherlands, Jan Oort had noticed something in a completely different context. Oort was studying the motions of stars in the disk of the Milky Way, not their orbits around the centre, but their small oscillations up and down, above and below the plane of the galaxy. A star that rises out of the disk is pulled back down, and how fast it is pulled back depends on how much mass is in the disk beneath it. Oort measured those vertical motions, and concluded that the disk contained more mass than the visible stars could account for. It became known as the Oort discrepancy. That one, as it happens, was mostly a false alarm. Later measurements, with better data on faint stars and interstellar gas, closed most of the gap with ordinary matter that had simply been undercounted. The Oort discrepancy was not, in the end, evidence for dark matter, but it is a useful reminder that missing mass in the 1930s was a thing that turned up occasionally and usually went away again when someone counted more carefully. That was the reasonable expectation. Most anomalies dissolve. Zwicky's did not, but nobody could know that yet. So the result was shelved, not refuted, not disproved, simply set down because there was nothing to do with it, and because the man who had produced it had spent a decade making sure that nobody wanted to help him. What is worth understanding about Zwicky is how often this happened to him, and how often he was right. In 1934, 1 year after the dark matter paper, he and Walter Baade published a 2-page abstract proposing that a supernova, a term they coined in that paper, was the transition of an ordinary star into a new kind of object, composed almost entirely of neutrons, which would be extraordinarily dense and extraordinarily small. The neutron had been discovered 2 years earlier. They were proposing an entire class of stellar corps, correctly, on the basis of almost nothing. Neutron stars were not observed for another 33 years. In 1937, he pointed out that a galaxy sitting in the line of sight to a more distant object would act as a gravitational lens, bending its light and possibly producing multiple images, and, further, that measuring that bending would allow astronomers to weigh the intervening galaxy directly, without any assumptions about its light. He said this was likely to be the best way to test his own dark matter claim. Einstein himself had published a note the year before, saying that gravitational lensing by stars would be far too small to ever observe. Zwicky said, "Not by stars, by galaxies, and then it will work." The first gravitational lens was observed in 1979. Gravitational lensing is now the single most important tool we have for mapping dark matter, and it is the technique that would eventually produce the decisive image. It was in the plan, in print, in 1937, from the man nobody would listen to. He also spent decades compiling a 6-volume catalogue of galaxies and clusters, largely alone, and it remained a standard reference long after his death. He proposed, apparently seriously, that humanity could reshape the solar system by firing projectiles at the sun to steer it. That one has not aged as well. Something else is worth saying about the 40 years the problem spent on the shelf, because it was not entirely empty. In 1959, 2 astronomers named Franz Kahn and Lodewijk Volcher noticed a small oddity in the local neighbourhood. The universe is expanding. Almost every galaxy we look at is receding from us. Its light shifted toward the red, and the further away it is, the faster it goes. This is the basic observational fact of cosmology. Andromeda is coming toward us. It is approaching the Milky Way at about 110 kilometers per second, and it will arrive in a manner of speaking in about 4 billion years, which means that at some point in the past, the 2 galaxies must have been moving apart, carried by the expansion, and then gravity between them overcame that expansion, reversed it, and pulled them back toward each other. Kahn and Volcher did the obvious calculation. Given the distance between the 2 galaxies, and given the age of the universe, how much mass would the pair need to contain for gravity to have reversed their separation in the time available? The answer they got was several times more mass than the 2 galaxies visibly contain. It is a beautifully simple argument. It uses no telescope beyond a spectrograph, no exotic physics, nothing but the age of the universe, and the fact that our neighbour is falling toward us instead of running away. It is now called the timing argument, and it gives a mass for the local group of something like 2 or 3 trillion suns, several times more than the stars can account for. Nobody built a research program around it. It was a curiosity, a footnote, one more small anomaly in a decade that had plenty. But it was there, in 1959, quietly saying the same thing as the Coma cluster. There is more mass here than there is light. The pattern is worth noticing. The evidence for dark matter did not arrive as a single discovery. It accumulated as a series of unrelated inconveniences, each one small enough to be set aside, each one arising from a different kind of measurement, each one saying the same thing to nobody in particular. A cluster that moves too fast, a pair of galaxies falling together too hard, a disk that should tear itself apart and does not. It took decades before anyone stood far enough back to see that all the anomalies were the same anomaly. Zwicky himself did not live to see the picture assembled. He died in 1974 in Pasadena. By then, the missing mass problem was back reopened by an entirely different kind of observation, by a person who could not have been less like him. He lived just long enough to see it happen, and there is no record that he was gracious about it. The observation that reopened it was not made in a cluster of galaxies at all. It was made inside single galaxies, one at a time, by measuring the speed of the stars going around. 3. Rubin and the curve that refused to fall. Vera Rubin wrote to Princeton in 1948 to request a graduate catalogue for the astronomy department. They did not send her one. They wrote back to explain that the department did not accept women and that there was therefore no point in her having the catalogue. Princeton did not admit a woman to its graduate astronomy program until 1975. She went to Cornell instead, where her husband was a graduate student in physics, and where she found herself in a department that included Hans Bethe, who had worked out how stars burn, Philip Morrison, and Richard Feynman. For her master's thesis, she looked for something no one was looking for: a large-scale motion of galaxies over and above the general expansion of the universe, a bulk flow, a sideways drift of the whole neighbourhood. She presented it at a meeting of the American Astronomical Society in 1950. She was 22 years old, and she had given birth to her first child a few weeks earlier. The reception was cold. The idea was dismissed, the data called insufficient, the whole thing regarded as slightly embarrassing. Large-scale coherent flows of galaxies are now an accepted part of cosmology. We know the local group is being pulled at hundreds of kilometers per second toward a concentration of mass in the direction of Centaurus. Rubin was 30 years early, with poor data, and she was told to sit down. She did her doctorate at Georgetown, under George Gamow, on the clustering of galaxies, another early idea, another cool reception. And then she made a decision that she later described very plainly. She was tired of controversy. She wanted to work on something so unglamorous, so uncontested, so quietly technical that nobody would fight her about it. She chose the rotation of spiral galaxies. The instrument that made it possible belonged to a man named Kent Ford. Ford was an instrument builder at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, and he had built a spectrograph with an image tube, an electronic device that amplified faint light before it reached the photographic plate. The gain was enormous. Exposures that would once have taken all night could be done in an hour. Regions of a galaxy so dim that they had previously been unmeasurable now gave up a spectrum. Rubin and Ford took that instrument to the telescopes at Kitt Peak and Lowell and Palomar and pointed it at Andromeda. The technique is straightforward to describe. You place the slit of the spectrograph across the galaxy, running out from the bright center along the disk. You collect the light, then you look at where the spectral lines fall, the dark absorption lines of hydrogen and nitrogen and sulfur that appear at precisely known wavelengths in a laboratory. If a region of the galaxy is moving toward you, its lines shift blue. Away, red. The size of the shift gives you the speed. Do this at many points along the slit, and you have a rotation curve, a graph of orbital speed against distance from the center. What should the graph look like? Look at the solar system. Almost all the mass is at the center, in the Sun. Mercury, close in, is deep in that gravitational well and moves fast, about 48 kilometers per second. Earth further out moves at 30, Jupiter at 13. Neptune, far out at the edge, crawls at 5.5. Orbital speed falls with distance, because the further you go, the weaker the pull of the central mass. This is Kepler's pattern, and it has been known for 400 years. A spiral galaxy looks like it should behave the same way. The light is concentrated in the middle. There is a bright, dense central bulge, and then a disk that thins and fades as you move outward until it disappears into the dark. If the mass follows the light, and why would it not? Since the light comes from stars, and stars are what a galaxy is made of, then the outer stars should be orbiting a distant central concentration, and they should be slow. Rubin and Ford measured Andromeda outward from the center. The speed climbed quickly, as expected, through the inner regions, and then it stopped climbing, and it did not come down. Out through the disk, further and further from the center, past the point where the light was fading to nothing, the stars and the gas kept moving at roughly the same speed, around 230 kilometers per second, as though they were not orbiting a central mass at all. The curve went flat. It went flat and it stayed flat, all the way to the edge of what the instrument could see. Rubin's first instinct was that Andromeda might be peculiar. Galaxies are individual objects. One of them can be strange. So they moved to another, flat, another, flat. Another. They worked through the spirals, one at a time, Over several years, 60 of them, and then more, spanning a wide range of sizes and brightnesses and types. Every single one was flat. There are only two ways to read that graph, and Rubin knew both of them from the beginning. Either Newton's law of gravity, which had been tested to exquisite precision within the solar system, fails at the scale of a galaxy, or the mass of a galaxy does not follow its light. The visible galaxy, the beautiful spiral in the photograph, is sitting inside something much larger and much heavier that does not glow. She was, by temperament and by experience, reluctant to claim that Newton was broken. She reported what she measured. She was extremely careful about the data, which is the reason it held. She was also not alone, which is the reason it was believed. At almost the same time, radio astronomers were doing the same thing with a different tool and getting the same answer. Neutral hydrogen gas emits at a wavelength of 21 centimeters, and that gas extends far beyond the visible stellar disk, sometimes 2 or 3 times as far. Radio telescopes could therefore measure rotation speeds in regions where there were no stars at all to measure. Morton Roberts in the United States had already found, using this method, that Andromeda's rotation stayed flat far outside its optical edge. And in 1978, a Dutch graduate student named Albert Bosma completed a doctoral thesis at Groningen that mapped the hydrogen rotation curves of 24 spiral galaxies out to enormous radii. They were flat, all of them, out into the darkness, where there was nothing to see. The gas was still going round at full speed, held by something, and the theorists had already worked out, independently, that this had to be true. In 1973, Jeremiah Oestreicher and Jim Peebles at Princeton ran computer simulations of a rotating disk of stars, a model galaxy, and found that it was violently unstable. Left to itself, a self-gravitating disk collapses into a bar within a couple of rotations. It does not stay a graceful spiral. The only way they could stabilize the simulation was to embed the disk inside a massive, roughly spherical halo of unseen matter, a halo containing considerably more mass than the disk itself. Without a halo, the galaxies in the sky should not look like the galaxies in the sky. So by the end of the 1970s, there were 3 lines converging from 3 directions. The optical rotation curves, the radio rotation curves reaching further out, and the stability argument saying that spiral galaxies could not survive as spirals without a halo. Add Zwicky's clusters, sitting in the literature for 40 years, saying the same thing on a larger scale. The community accepted it. Not with a single dramatic moment of conversion. There was no press conference, no single decisive paper, but over a few years in the late 1970s and early 80s, invisible mass moved from an eccentric claim to a working assumption. By 1980, a person could say in a seminar that galaxies were embedded in dark halos and expect nods rather than arguments. The shape of that halo is worth holding on to, because it is not what people picture. The Milky Way's dark matter halo is not a shell around the galaxy, and it is not a ring. It is a roughly spherical cloud, densest toward the center, and thinning gradually outward. And the visible galaxy, the disk, the arms, the 200 billion stars, the entire object that shows up in every photograph is a thin, luminous wafer sitting in the middle of it. The halo extends perhaps 10 times further out than the disk. Most of the Milky Way, by mass and by volume, is dark. The bright part is a detail near the center. We can now do to our own galaxy what Rubin did to Andromeda, and we do it with a spacecraft. The Gaia Observatory, launched by the European Space Agency in 2013, sits at a gravitationally quiet point about 1.5 million kilometers from Earth, and it has spent more than a decade doing one thing, measuring the positions, distances, and motions of stars. Not a handful of stars, nearly 2 billion of them. It measures the tiny apparent shift of each star's position as the Earth moves around the Sun, which gives a distance, and it measures the star's drift across the sky year on year, which gives a velocity. The result is a 3-dimensional map of a substantial fraction of the Milky Way, with motion attached to every point. From that map, the rotation curve of our own galaxy can be drawn not inferred from the light of a distant spiral, but measured directly, star by star, from the inside. It behaves exactly as Rubin's galaxies behaved. It rises, it flattens, it stays flat far out into the disk, and at the largest radii that can be measured, it declines only very gently, far more gently than the visible mass allows. The map also lets astronomers weigh the halo a second way, by asking which stars are moving fast enough to leave. There is an escape velocity from the Milky Way, just as there is from the Earth, and it depends on the total mass. Find the fastest moving stars in the local neighbourhood, the ones that are on the edge of being flung out of the galaxy entirely, and you can work out how deep the well they are climbing must be. The answer comes to somewhere in the region of 1 trillion solar masses for the total mass of the Milky Way. The stars account for perhaps 60 billion of that. The gas? A little more. The rest is dark. There is a third method, and it involves watching a small galaxy being destroyed. The Sagittarius Dwarf is a satellite galaxy of the Milky Way, and it is currently being torn to pieces. It has passed through our disk several times, and on each passage the tidal forces have stripped stars out of it, leaving behind long streams of debris that now wrap more than once around the entire sky. Those streams are not smooth. They bend and twist, and the shape of the bending depends on the shape of the gravitational field they are moving through, which means the stream is a probe. It is a line of test particles laid down over billions of years, tracing the geometry of the dark halo far beyond anything we could reach by other means. Model the stream, and you learn the shape of the invisible thing. It is falling through whether the halo is spherical, or flattened, or lumpy. The answer, so far, is that it is roughly spherical, somewhat flattened, and that it extends far beyond the visible galaxy, and that it contains most of the mass of the object we live in. That is the thing to hold when you go outside and look up at the band of the Milky Way on a clear night. You are not looking at the galaxy. You are looking at the part of it that happens to glow a thin, bright disk suspended in the middle of something roughly spherical, 10 times larger, several times heavier, and completely invisible, in every direction, all the way around you. Vera Rubin spent the rest of her career measuring galaxies. She discovered a galaxy in which half the stars orbit in one direction and half in the other, which is exactly the kind of object nobody expects to exist. She was elected to the National Academy of Sciences. She spent decades quietly and persistently pushing to get women into observatories that had not previously admitted them, including one famous instance in which she was told that a facility could not host her because it had no women's bathroom, and she went to her room, cut a paper skirt out of a diagram, taped it to the stick figure on a door, and said that now it did. She never received the Nobel Prize. She died in December 2016, at the age of 88. What she had shown was that the missing mass was not a peculiarity of a distant cluster. It was in every galaxy. It was in the one we live in. It was overhead, but there was still a way out, and for a long time it was a serious way out. 4, the other answer, and the image that ended it. Here is the way out. Every argument for dark matter has the same structure. We observe motion. We calculate the gravity required to produce that motion. We compare it with the gravity we can account for from visible mass. There is a shortfall. We conclude that there is invisible mass. But that conclusion rests on a step that nobody checked, because nobody thought it needed checking, that we know the law of gravity out there. The rotation curve of a galaxy is not evidence for missing mass, unless Newton's law is correct at those distances and those accelerations. And it had never been tested at those distances or those accelerations. Not once. In 1983, an Israeli physicist named Mordechai Milgrom at the Weizmann Institute published 3 papers proposing exactly that. He suggested that the missing mass was not missing at all, that our law of gravity simply fails in a regime we had never probed. The regime is not defined by distance, it is defined by acceleration. Milgrom noticed that the flat rotation curves always appear once the gravitational acceleration of a star drops below a particular threshold, a value of about 1.2 times 10 to the minus 10 meters per second squared. That is an almost absurdly small number. It is roughly 1/10 billionth of the acceleration you feel standing on the Earth. It is the acceleration that would take you a year to reach walking pace. In the inner regions of a galaxy, accelerations are above that threshold, and Newton's law works perfectly. Beyond it, Milgrom proposed, gravity stops falling off the way, Newton says, and falls off more slowly, clinging to the outer stars, holding them at speed, producing a flat rotation curve with no dark matter at all. He called it modified Newtonian dynamics. MOND. It is easy to describe MOND as a fringe theory and move on, and that would be dishonest. It has one property that has never been fully explained by the competing picture, and that property is uncomfortable. MOND has a single free parameter, the acceleration threshold. One number, fixed once, for all of physics, and with that one number, from the distribution of visible matter alone, it predicts the full rotation curve of a spiral galaxy. Not fits it after the fact, predicts it. Give MOND a photograph of the stars and gas in a galaxy, and it will tell you how fast the outer material is moving, and it will be right, and it will be right for large galaxies and small galaxies, for bright ones and for faint low-surface brightness ones, where the dark matter picture says the visible stars are almost irrelevant. This shows up in the data as a very tight relationship, now called the radial acceleration relation. Across hundreds of galaxies, the acceleration you actually measure at any point in a galaxy is determined, almost perfectly, by the acceleration you would calculate from the visible matter alone. There is barely any scatter. The visible matter appears to know exactly how much dark matter is supposed to be around it. That is strange. In the dark matter picture, a galaxy's halo forms first, out of a substance that does not talk to ordinary matter at all, and the ordinary matter then falls in afterwards and does complicated, messy, unpredictable things. It cools, it forms stars, it explodes, it drives winds. There is no obvious reason why the messy visible part should end up in such a clean, tight, universal relationship with the invisible part. Simulations can now reproduce the relation, more or less, but it required work, and there are people who still find the tightness of it suspicious. Milgrom's formula gave it for free in 1983. So MOND is not stupid. It is a serious idea that gets one thing right, that the standard picture gets right only with effort. It gets almost everything else wrong. Start with clusters. Apply MOND to the coma cluster, to the very system Zwicky measured, and the modification helps but not enough. You still need to add missing mass, roughly a factor of 2 of it, to hold the cluster together. A theory invented specifically to abolish dark matter turns out to require dark matter in exactly the place where dark matter was first proposed. That is not a fatal objection to some more sophisticated version of the idea, but it is not a small problem either. Then, there is the deeper structural issue. MOND, as Milgrom wrote it, is not a theory. It is a formula. It modifies Newton's law, and Newton's law is itself only an approximation to general relativity, which is what actually governs gravity. A modification of Newtonian dynamics that does not also tell you how to modify. Einstein cannot describe the bending of light, cannot describe the expansion of the universe, cannot describe the early cosmos. Einstein, Jacob Bekenstein, produced a relativistic version in 2004, a considerably more complicated theory with extra fields bolted on to make it work. Others followed. They are not elegant, and the elegance was the whole selling point. And then, in 2006, a photograph. There is an object about 3.7 billion light-years away, in the southern constellation Carina, which is not one galaxy cluster but 2. They have collided. Roughly 150 million years ago, a smaller cluster passed through a larger one at a relative speed of several thousand kilometers per second, and we are seeing the aftermath from almost exactly side on. The shock wave in the gas has a distinctive bullet shape, which is where the name comes from, the bullet cluster. What makes it useful is that a galaxy cluster is made of 3 things, and a collision separates them. There are the galaxies themselves, which sound like the main event, and are not. They contribute only a small fraction of the mass, and galaxies are mostly empty space. When 2 clusters collide, the individual galaxies almost never hit each other. They sail straight through like 2 swarms of gnats passing through one another, essentially undisturbed. Then there is the hot gas. This is where most of the ordinary matter in a cluster actually lives, not in the stars, but in a diffuse plasma at tens of millions of degrees, filling the space between the galaxies, glowing brilliantly in X-rays. It outweighs all the stars in all the galaxies of the cluster by a factor of several, and gas, unlike galaxies, cannot pass through gas. It collides, it shocks, it heats, it experiences drag. And then there is whatever else is there, the missing mass, the thing that makes up the majority of the cluster's gravity. So a team led by Douglas Clow and Marusha Bradach did the experiment that the collision had set up for them. They observed the bullet cluster in X-rays using the Chandra X-ray Observatory, which showed them exactly where the hot gas was. And they observed it with the Hubble Space Telescope and ground-based instruments, and used gravitational lensing, Zwicky's technique, the one he had proposed in 1937 for precisely this purpose, to map where the mass was. Distant background galaxies, far behind the cluster, have their images subtly stretched and distorted by the cluster's gravity, and from the pattern of that distortion you can reconstruct the mass distribution without any assumption about what the mass is made of or whether it emits anything. Two maps, one of the ordinary matter, one of the gravity. If the missing mass is really missing, if there is no dark matter, and gravity simply behaves differently than we think, then the gravity must be produced by the ordinary matter because there is nothing else there to produce it. In that case, the lensing map must peak where the ordinary matter is, and the ordinary matter, overwhelmingly, is the hot gas, which the collision has stripped out and left stranded in the middle. That is not what they found. The two maps do not line up. The X-ray gas sits in the center, slowed and shocked, and left behind. The gravitational mass sits in two clumps well ahead of it, traveling with the galaxies, which pass through without stopping. The gravity has separated from the ordinary matter. It has gone somewhere else. It moved through the collision without noticing that a collision was happening, which is exactly what a cloud of particles that interacts only through gravity would do, and exactly what a modified law of gravity, anchored to the visible stuff, cannot do. That image is the reason most physicists stopped considering modified gravity a live alternative, not because it is a knockdown proof. MOND advocates have proposed responses, mostly involving additional unseen mass, which somewhat defeats the purpose, but because it changes the character of the question. Dark matter stopped being a bookkeeping discrepancy and became a substance with a location, something that can be somewhere, something you can point at on a map and say, it is there and the gas is over there and they have come apart. Honesty requires one more object. There is another colliding cluster, catalogued as Abel 520 and known informally as the train wreck, where the analysis gives a confusing result. A concentration of dark mass that appears to sit with the gas in the middle, rather than moving ahead with the galaxies. If that reading is correct, it is difficult to explain with a collisionless particle. The measurement is contested. Different teams analyzing the same system have reached different conclusions, and the mass reconstruction in a messy multi-way collision is genuinely hard. It has not overturned anything, but it is there, and it does not fit, and I would rather tell you about it than pretend the picture is seamless. The final blow to most modified gravity theories came from an entirely unexpected direction, and it took less than 2 seconds. In August of 2017, the gravitational wave detectors picked up the collision of two neutron stars in a galaxy about 130 million light-years away. 1.7 seconds after the gravitational wave signal ended, a gamma-ray burst arrived from the same patch of sky. Two messengers, gravity and light, launched by the same event, having raced each other across 130 million years of space and arriving within 2 seconds of each other, which means gravitational waves travel at the speed of light to a precision of about 1 part in 1,000 million. Many of the relativistic modified gravity theories, the ones built to give MOND a proper foundation, had required gravity to propagate at a different speed from light. In the days after that event, a whole class of them died. They were not argued out of existence, they were simply measured out of it. So the balance stands where it stands. Modified gravity explains one thing beautifully and everything else badly. Dark matter as a particle explains everything else beautifully, and that one thing only with effort. The weight of evidence has tilted heavily toward the particle, and the particle has not been found, which leaves an awkward question. We have spent an hour on the 85%. What about the 15? What about the ordinary matter, the atoms, the calcium, the iron, the thing you are made of? Where did that come from? And how do we know it is only 15%? 5, the 15%. And the woman who was made to disown her answer. For most of human history, nobody knew what the sun was made of. In 1835, the French philosopher Auguste Comte used the composition of the stars as his example of something that would forever be beyond knowledge, a thing about which we could speculate but never learn. Within a few decades, Spectroscopy had begun to answer it. The method is simple in principle. Pass starlight through a prism, and it spreads into a band of colour. And across that band are dark lines, narrow gaps where light is missing, because atoms in the star's outer atmosphere have absorbed it at precisely those wavelengths. Each element has its own pattern of lines, a fixed signature, unchanging. Sodium, here. Calcium, here. Iron in a dense thicket. Read the lines, and you can name the elements. By the early 20th century, astronomers had catalogued the lines in thousands of stellar spectra. The lines of iron were strong. The lines of calcium were strong. The lines of hydrogen were present, and everybody knew they were present, but they did not dominate the picture. The natural conclusion, the one almost everyone reached, was that the sun and the stars were made of roughly the same stuff as the Earth. Iron, silicon, oxygen, magnesium, in different proportions perhaps, but recognizably the same materials. The reason this was wrong is subtle, and it is the whole story. The strength of a spectral line does not tell you how much of an element is present. It tells you how much of that element is present in the particular state that can absorb that particular wavelength. And whether an atom is in that state depends on temperature and pressure, on how many of its electrons have been stripped away, and which energy level the remaining ones are sitting in. Hydrogen, the simplest atom, is peculiar in this respect. In a stellar atmosphere at a few thousand degrees, only a tiny fraction of hydrogen atoms are in the state that produces the visible absorption lines. A hydrogen line of a given strength, therefore, implies an enormous number of hydrogen atoms, far more than a similar strength iron line implies iron atoms. The equation that quantifies this had been worked out in 1920 by an Indian physicist named Meghnad Saha, who had grown up the son of a shopkeeper in a Bengali village and been thrown out of school as a boy for taking part in a boycott of a visiting British governor. His ionization equation connected the temperature and pressure of a gas to the fraction of its atoms in each state of excitation. It was the missing key. It converted line strengths into abundances. It was there, in the literature, waiting to be applied to the stars. Cecilia Payne applied it. She was English, born in Buckinghamshire, and she had gone to Cambridge to read natural sciences, where she attended a lecture by Arthur Eddington on the eclipse expedition that had just confirmed general relativity. She said afterwards that she did not sleep for 3 nights, that her world had been so shaken that she experienced something close to a nervous breakdown, and that she could have written the whole lecture out from memory. Cambridge did not, at that time, grant degrees to women. She completed her studies and left without one. She went to Harvard, to the observatory, where a fellowship existed for women, and where there was something that existed nowhere else in the world: 500,000 photographic glass plates, the accumulated spectra of hundreds of thousands of stars, collected and catalogued over decades, largely by a group of women employed to do the classification work for very little money. The plate collection was the best data set in astronomy. It was sitting there. Payne took Saha's equation, took the atomic theory that Niels Bohr and others had recently built, and worked through the spectra star by star, computing what abundance of each element would be required to produce the observed line strengths at the temperature each star's spectrum implied. The pattern that came out was consistent across every star she examined. Iron, calcium, silicon, magnesium, all present, all in roughly the proportions everyone expected relative to one another, all fine. And hydrogen was 1,000,000 times more abundant than any of them. Helium, likewise, was enormously more abundant than the heavy elements. Together, hydrogen and helium made up virtually the entire mass of a star. Everything else, every element that makes up rock and metal and water and bone, was a trace contaminant, a dusting on the surface of an ocean. The Earth is not a typical sample of the universe. The Earth is the leftover residue. The universe is hydrogen, with some helium in it and a rounding error of everything else. She wrote this up as her doctoral thesis in 1925. It was sent, as was customary, to Henry Norris Russell at Princeton, the most powerful astronomer in America, the man whose name is on the diagram every astronomy student still learns. Russell told her the hydrogen result was impossible. He did not tell her it was miscalculated. He could not find an error. He told her it was clearly not real, because it contradicted everything known about stellar composition, and he advised her not to publish it as a conclusion. She was a graduate student, 25 years old, foreign, female, without a degree from her own country, entirely dependent on the goodwill of the American astronomical establishment for any career at all. She added a sentence to her thesis saying that the enormous abundances derived for hydrogen and helium were almost certainly not real. She had the answer. She wrote it down, and then she was made to add a line saying it was probably wrong. 4 years later, Russell arrived at the same conclusion himself, by a different route using different data. He published it. He acknowledged Payne's earlier work in the paper properly, explicitly, in print. It made no difference to how the discovery was remembered. For decades, the result was attributed to Russell, and Payne's thesis, which Otto Struve later called the most brilliant doctoral dissertation ever written in astronomy, sat as a footnote to it. She stayed at Harvard for the rest of her life. For years, she was paid so little that her salary was recorded under equipment expenses. She was not given the title of professor until 1956, more than 30 years after the thesis, at which point she became the first woman to be made a full professor in the faculty at Harvard, and shortly afterwards the first to chair a department there. Now hold her result next to the dark matter problem, because they connect in a way that is not obvious. Payne established that the visible universe is overwhelmingly hydrogen and helium. That raises the question of where the hydrogen and helium came from, and the answer, worked out over the following decades, is that they were not made in stars at all. They were made in the first few minutes of the universe, in a period called primordial nucleosynthesis, when the entire cosmos was hot and dense enough to be a fusion reactor. That process ran for about 20 minutes and then shut off as the universe expanded and cooled. It produced hydrogen, a great deal of helium, a trace of lithium, and a small quantity of deuterium-heavy hydrogen, a proton with a neutron attached. Deuterium is the useful one. It is fragile. It is destroyed inside stars rather than created, and the amount that survived from the early universe depends with great sensitivity on one thing: how many protons and neutrons there were packed into a given volume in those 20 minutes. A denser early universe burns more of its deuterium into helium. A sparser one leaves more behind. So if you can measure how much deuterium there is in the universe today, and you can, by looking at the absorption spectra of gas clouds sitting in front of distant quasars, gas that has never been inside a star and never been processed, then you can calculate the total density of ordinary matter in the cosmos. All of it. Not just the shining part. Every proton and neutron in existence, whether it is in a star or a planet or a cold cloud of gas or a burnt-out cinder in the dark, the answer comes out at about 5% of the total energy density of the universe. That number is derived entirely from nuclear physics and the chemistry of the first 20 minutes. It has nothing to do with rotation curves, nothing to do with galaxy clusters, nothing to do with gravitational lensing, and it says that the total amount of ordinary matter available in the universe, including all the ordinary matter that is dark, all the dead stars and cold gas and rogue planets, and everything else that does not shine, is nowhere near enough to explain the gravity we measure. That is the sentence that closes the door. It means dark matter cannot be made of protons and neutrons. Whatever it is not a form of ordinary matter that we simply have not spotted. There are not enough protons in the universe. There never were. Whatever is holding the galaxies together is something that was not made in the first 20 minutes and is not built from the same parts as you. Cecilia Payne was not thinking about any of this. She was reading glass plates in a basement in Cambridge, Massachusetts, in 1925, and working out that the stars are mostly hydrogen. But the road from her thesis leads directly to the statement that the substance filling your bedroom tonight is not any kind of matter that has ever been catalogued. And it leaves us with a smaller and much more personal question. The heavy elements, the trace dusting, the contaminant, the calcium and the iron and the oxygen and the carbon that make up a body were not there at the beginning. They had to be made somewhere. 6. The Forge. In 1930, a 19-year-old physics graduate boarded a steamship in Madras, bound for England, to take up a place at Cambridge. The voyage took about 3 weeks. Subramanian Chandrasekhar spent it doing a calculation. He had been thinking about white dwarfs, the small, dense, faintly glowing corpses left behind when an ordinary star exhausts its fuel. A white dwarf has roughly the mass of the Sun packed into a sphere about the size of the Earth. Nothing is burning inside it. There is no fusion, no energy source, no outward pressure from heat. So what holds it up? Why does it not simply collapse? The answer, worked out in the 1920s, is a purely quantum effect. Electrons obey an exclusion principle. No two of them can occupy the same quantum state. Squeeze a gas of electrons into a small enough volume, and they run out of available states. And they resist further compression not because they repel each other electrically, but because there is nowhere left for them to go. This resistance is called electron degeneracy pressure, and it has nothing to do with temperature. A white dwarf can cool to absolute zero, and it will still hold itself up. Chandrasekhar added one thing to that picture. He asked what happens when the electrons are pushed so hard that they are moving at speeds approaching the speed of light. Relativity changes the arithmetic. As the electrons become relativistic, the pressure they can supply grows more slowly with density than the Newtonian calculation says. Gravity, meanwhile, keeps growing. Somewhere, the two curves cross. Somewhere, there is a maximum mass beyond which degeneracy pressure loses. He found it on the ship, about 1.4 times the mass of the Sun. Above that, nothing stops the collapse. Not heat, not quantum mechanics, not anything he could identify. The star simply keeps falling inward. He arrived in England, worked it up properly, and presented the full result to the Royal Astronomical Society in London in January of 1935. He was 24. When he finished, Arthur Eddington, the most eminent astrophysicist in Britain, the man who had confirmed general relativity, the man whose lecture had shaken Cecilia Payne so badly that she could not sleep, stood up and ridiculed him in front of the room. Eddington said there ought to be a law of nature to prevent a star from behaving in this absurd way. He said the result was a reductio ad absurdum of relativistic degeneracy. He was charming and he was funny and he was completely wrong, and the audience, which was not competent to judge the mathematics, took Eddington's side because Eddington was Eddington. Chandrasekhar had discussed the calculation with Eddington repeatedly in the weeks before, and Eddington had never once said he disagreed. He had let him walk into it. Chandrasekhar was right. Every part of it was right. The limit that bears his name is a fixed and central number in astrophysics. But the encounter effectively ended his working relationship with British astronomy. He left for the University of Chicago in 1937, and he did not return to the subject of stellar collapse for decades. He received the Nobel Prize in 1983, 48 years later. Now follow the consequence. A star like the Sun will never approach that limit. It fuses hydrogen into helium in its core for about 10 billion years, currently at a rate of 600 million tons of hydrogen per second, 4 million tons of which is converted directly into energy and leaves as light. When the core hydrogen runs out, the star swells into a red giant, briefly fuses helium into carbon and oxygen, and then, lacking the mass to go further, sheds its outer layers as a glowing shell of gas and leaves behind a white dwarf about the size of the Earth. It will sit there and cool for a length of time longer than the current age of the universe. It will never make iron. It will never make gold. There is a story worth telling about that sunlight, because it is the one time we succeeded at something like the search we are still failing at. Fusion in the Sun's core produces neutrinos, and neutrinos, unlike photons, escape immediately. The light we see left the core as gamma rays and spent something like 100,000 years fighting its way outward through the dense interior, scattering endlessly before reaching the surface. The neutrinos take about 2 seconds, then 8 minutes to Earth, which means neutrinos are the only way to see the core of a star as it is now, rather than as it was 100,000 years ago. In the 1960s, a chemist named Raymond Davis set out to count them. He filled a tank with 100,000 gallons of dry cleaning fluid perchloroethylene because it is full of chlorine, and a neutrino striking a chlorine atom will very occasionally convert it into an atom of argon, and he put the tank a mile underground in a working gold mine in South Dakota to shield it from cosmic rays. The mine was called Homestake. It is the same mine that now houses the LZ dark matter detector, the same shaft, the same rock, 60 years apart, the same reason. Davis then had to extract, from 100,000 gallons of fluid, the handful of argon atoms produced over the course of a month. Not a handful in a scientific sense. A literal handful, about 1 atom every 2 days. He did it by bubbling helium through the tank and trapping what came out, and he counted individual atoms, and the technique was so absurd that a great many people believed it could not possibly work. It worked. He found neutrinos from the Sun. he found about a third as many as the theory predicted. The deficit was called the solar neutrino problem, and it sat unresolved for 30 years. Either Davis's experiment was wrong, or our model of how the sun burns was wrong, and neither seemed likely, and no amount of checking made it go away. The answer, confirmed in 2001 at an observatory 2 kilometers underground in a Canadian nickel mine, was that neither was wrong. There are 3 types of neutrino, and Davis's tank could only detect one of them. Neutrinos change type in flight. 2/3 of the sun's neutrinos were arriving at the Earth as something Davis's chlorine could not see. For that to happen, neutrinos must have mass, which the standard theory of particle physics had said they did not. Davis received the Nobel Prize in 2002, aged 87, for an experiment he had begun 40 years earlier, and which had been widely regarded, for most of that time, as a mistake. It is worth holding that next to the empty xenon tanks. He looked for something almost undetectable, found the wrong number, was disbelieved, and was right, and the resolution required a fundamental revision of particle physics. Neutrinos, incidentally, are not the dark matter. They have mass, and they are everywhere, but the mass is far too small, and they move far too fast to clump into halos. They were checked. They were eliminated. That is what the process looks like when it works. A star of 8 solar masses or more does something else entirely. Its core is hot enough and heavy enough to keep going. When hydrogen runs out, it burns helium. When helium runs out, it burns carbon, then neon, then oxygen, then silicon. Each stage produces a heavier ash, and each stage requires a hotter core, and the star builds itself into a layered structure, hydrogen burning in a thin outer shell, helium beneath it, then carbon, neon, oxygen, silicon, each in its own zone, like the layers of an onion. The timescales are the thing worth holding on to here. For a star of about 20 solar masses, hydrogen burning lasts around 10 million years, helium burning about 1 million, carbon roughly 1,000 years, neon about a year, oxygen a few months. Silicon burning lasts about 1 day. In that final day, the star fuses silicon into iron and nickel, and it builds an iron core at its center, growing by fractions of a solar mass per hour. And iron is the end of the road. Iron has the most tightly bound nucleus in nature. Fusing iron into anything heavier does not release energy, it consumes it. The furnace that has held the star up for 10 million years reaches a fuel that will not burn. The iron core grows until it crosses the Chandrasekhar limit. And then, exactly as the boy on the steamship calculated, degeneracy pressure fails. The collapse takes less than a second. The inner core falls inward at something like 1/4 of the speed of light. Electrons are crushed into protons, converting them into neutrons and releasing a flood of neutrinos. Within milliseconds, an object the size of the Earth has become a sphere of nearly pure neutrons about 20 kilometers across, so dense that a teaspoon of it would weigh 1 billion tons. And at that density, the neutrons themselves become degenerate, and the collapse stops violently. The core bounces. The outer layers of the star, which are still falling in, meet the rebounding core and a shockwave forms. And here the modelling gets difficult, because for decades the calculations showed that the shockwave stalls, it runs out of energy, it does not blast the star apart, and the simulated supernova simply fails. What saves it, in the current understanding, is the neutrinos. The collapsing core releases an amount of energy that is genuinely difficult to hold in the mind. About 99% of the total energy of the supernova leaves as neutrinos, particles that barely interact with anything at all. The light, the blinding flash that outshines an entire galaxy for weeks, is about 1% of it. The kinetic energy of the exploding star is about 1% of it. The rest is neutrinos, streaming out through the collapsing star, and a small fraction of them are absorbed on their way out. And that small fraction reheats the stalled shock and drives the explosion. We know that this is true because we have watched it happen. On the 23rd of February, 1987, a star exploded in the Large Magellanic Cloud, about 160,000 light-years away. It was the closest supernova observed in nearly 400 years. And several hours before the light arrived, 3 neutrino detectors on Earth, a water tank in a Japanese mine, another in a salt mine under Lake Erie, and one in Russia registered a brief burst of neutrinos. 24 of them. 24 particles, out of an outpouring so vast that the number leaving the star is written with 57 zeros, and 24 of them happen to interact inside our tanks during a window of about 13 seconds. They arrived first because the neutrinos escape the collapsing core immediately, while the shockwave takes hours to fight its way out through the star before the light can emerge. The entire theory of core collapse, the neutrino flood, the timing, the energy was confirmed by 24 particles in a swimming pool. And in the explosion itself, in the fury of the shock front and the neutron-rich material blowing outward, something else happens. Nuclei are bombarded with free neutrons so rapidly that they capture them faster than they can decay, climbing the periodic table in seconds. This is the rapid neutron capture process, and it builds the elements that cannot be made in ordinary fusion. Silver, iodine, xenon, the same xenon that now sits in a tank under an Italian mountain, waiting. Gold, platinum, lead, uranium. For decades, it was assumed that supernovae made most of these. It is now clear that a great deal of the gold, in particular, comes from somewhere else, from the collision of two neutron stars, which flings out a spray of the densest material in the universe, neutron-rich and unstable, that decays into heavy elements as it goes. We watched this happen in August of 2017, the same event that killed the modified gravity theories. The gravitational wave detectors caught the merger. Telescopes around the world turned to the galaxy where it had occurred, and over the following days they watched the glow of freshly synthesized heavy elements, an amount of gold and platinum estimated in the range of several times the mass of the Earth, expanding into space. Every atom of gold that has ever been mined, worn, hoarded, or fought over was made in one of those two events. There is no other source, which brings this home quite literally. The calcium in your bones, the iron in your blood, which is what carries the oxygen you are breathing right now, the oxygen itself, the carbon that forms the spine of every organic molecule in your body, the phosphorus in your DNA, the zinc in your enzymes, none of it existed at the beginning. The universe produced hydrogen, helium, and a trace of lithium, and nothing else. Every atom in you heavier than those was assembled inside a star and released by a star's death before the sun existed. The sequence is not vague. A previous generation of massive stars formed in this region of the galaxy, lived for a few million years, built the elements in their cores, and exploded. Their debris expanded and mixed into the interstellar medium, some of that enriched material collected into a cold molecular cloud. About 4.5 billion years ago, a fragment of that cloud collapsed, quite possibly triggered by the shockwave of yet another nearby supernova, and formed the Sun and a disk of leftover debris around it, and out of that debris, the planets. The Crab Nebula, in the constellation Taurus, is what one of these events looks like 1,000 years on. In the year 1054, Chinese court astronomers recorded a guest star that appeared in that part of the sky and was bright enough to be seen in daylight for 23 days. What is left of it is a tangle of expanding filaments, still growing, and at the center a neutron star spinning 30 times a second, sweeping a beam across the Earth with each rotation. That object is a grave. It is also a factory, and it is the same kind of event that made the iron in the blood moving through your heart at this moment. That is the ordinary 5%, the part that shines, the part that builds, the part that can be traced. Now go back to the collapse, and consider what happens when the core that falls is heavier still, because the neutrons have a limit too. 7. The things that keep nothing. Neutron degeneracy pressure has a limit, in the same way that electron degeneracy pressure has a limit, and for the same reason. Somewhere above, about 2 solar masses, the exact figure is still being pinned down, and the gravitational wave observations are steadily narrowing it. The neutrons cannot hold either, and this time there is nothing underneath. No further quantum barrier, no new form of pressure waiting to catch the collapse. The core falls, and it keeps falling, and nothing in physics as we currently understand it stops it. The idea is older than you might expect. In 1783, an English clergyman named John Mickell, rector of a parish in Yorkshire and one of the more inventive minds of his century, wrote to the Royal Society with a thought experiment. Newton had treated light as a stream of particles. If light is made of particles, Michel reasoned, then gravity should act on it. and there should exist a star so massive that light thrown upward from its surface would fall back down. Such a body would be invisible. He calculated roughly how massive it would have to be, and he pointed out that although you could not see one, you might detect it by watching for a visible star orbiting an invisible companion. He called them dark stars. His method for finding them was exactly correct, and it is exactly how the first one was eventually found, nearly 200 years later. The idea then vanished for a century, because light turned out to be a wave, and nobody knew how gravity was supposed to pull on a wave. In November of 1915, Einstein presented the field equations of general relativity, which describe gravity not as a force, but as the curvature of space-time. Within weeks, a German physicist named Karl Schwarzschild, then serving as an artillery officer on the Russian front, calculating shell trajectories in the trenches, found an exact solution for the simplest possible case: a single spherical mass sitting in otherwise empty space. He sent it to Einstein, who was astonished that a solution had been found at all, let alone that fast, let alone from a war zone. The solution contained an oddity. At a particular distance from the mass, determined only by the mass, the mathematics broke down. Terms went to infinity. Schwarzschild noted it. Neither he nor Einstein believed it corresponded to anything physical. For an object like the Sun, the distance in question was about 3 kilometers, buried deep inside a body, 700,000 kilometers in radius, in a place where the solution did not apply anyway. It was a curiosity, an artifact, a place where the equations misbehaved. Schwarzschild died 4 months later of an autoimmune skin disease he contracted in the trenches. He was 42. The distance is now called the Schwarzschild radius, and we know what it is. It is the event horizon. It is not a surface. This is the thing people most consistently get wrong, and it is worth being careful about. If you were to travel toward a large black hole and cross the horizon, there would be nothing to see and nothing to feel. No wall, no membrane, no shimmer, no sensation of passing through anything at all. For a black hole of a few million solar masses, the tidal forces at the horizon are gentle. You would not be torn apart. Not there. Not yet. You would sail across a boundary that has no local existence whatsoever, and the only way you could know you had done it is by working out afterwards that you could not get back. Because that is what the horizon is. It is a statement about the future, not about a place. Inside it, the curvature of space-time is so severe that every possible path, every direction you could accelerate, every course you could steer, every trajectory available to anything moving at or below the speed of light leads inward. The center stops being a location you could travel to and becomes a moment you are traveling toward, in the way that next Tuesday is a moment you are traveling toward and cannot avoid, no matter which way you drive. Escape is not hard inside a black hole. It is not a question of insufficient thrust. There is simply no direction that points out. Try it from the inside. You are falling toward a black hole of about 4 million solar masses, the one at the center of this galaxy, the one the stars have been orbiting for as long as anyone has been watching. You are not in any danger yet. You are falling freely, which means you feel nothing at all. There is no wind, there is no sensation of speed. Weightlessness in a gravitational field is not the absence of gravity. It is the experience of surrendering to it completely. Ahead of you there is a black disk. It is not black in the way a painted surface is black. It is black in the way that a hole in a photograph is black. An absence with no texture and no depth, and around its edge a thin ring of light that should not be there, because it is light from stars that are behind the black hole, bent around it and delivered to your eye. You can see, at the rim, the sky from the other side. The whole sky is being pulled forward. As you accelerate, the stars ahead of you crowd together, blue-shifted, brightening, compressing into an ever smaller circle around the darkness. The universe behind you thins and reddens. You cross the horizon. Nothing happens. There is no boundary, no shock, no threshold. The instruments register nothing, because there is nothing local to register. You could not point to the moment it occurred. If you had been asleep, you would not have woken. What has changed is not around you, but ahead of you. Before, the center was a place somewhere out there, in a direction which you were choosing to approach. Now, it is a time. It is your future. in the same way that the next minute is your future, and you have exactly as much ability to steer away from it. There is no engine that helps. There is no direction that is away. The geometry has folded, and every path you could take, at any speed, with any amount of power, arrives at the same place. You have somewhere between a few seconds and a couple of minutes, depending on the mass. And then, at the end, the tides. The difference in gravity between your feet and your head becomes larger than the forces holding your body together, and then larger than the forces holding your cells together, and then the atoms. And then there is nothing left to speak of at all. Nobody has done this. Nobody will. But every step of it is a straightforward consequence of a set of equations written in a trench in 1915. And there is nothing in physics that suggests any part of it is wrong. Seen from outside, the picture is stranger still. If you watch a clock fall toward the horizon, you see it tick more and more slowly. Its light reddens, stretches, dims. It approaches the boundary and never arrives asymptotically slowing, fading toward invisibility, frozen at the edge. From the outside, nothing ever falls in. The infalling matter of the original collapsing star is still, in a sense, out there at the boundary, redshifted into darkness. And from the inside, the clock crosses without incident and reaches the center in a finite and rather short time. Both accounts are correct. They cannot be reconciled into a single narrative because they are not describing a single time. That is the actual content of general relativity, and this is the place where it stops being an abstraction. What happens at the center, we do not know. The equations say the density becomes infinite, and an infinity in a physical theory is not a result. It is a sign that the theory has been pushed beyond its domain and has broken. To describe the center of a black hole, you would need a theory that combines general relativity with quantum mechanics, and there is no such theory, not a contested one, not a leading candidate with rivals. There simply is not one. The first real black hole was found by accident, and Michel's method was what confirmed it. In 1964, a sounding rocket launched from New Mexico, carrying a crude X-ray detector. The flight lasted a few minutes above the atmosphere, which is all you can get from a rocket. It found a fiercely bright X-ray source in the constellation Cygnus, and the source was named Cygnus Zon. Later observations showed it flickering on timescales of 1/100th of a second, which sets a hard limit on its size. Nothing can vary faster than light can cross it, so the emitting region had to be smaller than a few thousand kilometers. Then astronomers found a blue supergiant star in exactly that position, a large, hot, ordinary star, and the supergiant was wobbling. It was orbiting something every 5.5 days, and from the orbit they could weigh the companion. The companion was invisible, and it was heavy. Modern estimates put it at about 21 times the mass of the Sun. A white dwarf cannot be that massive. A neutron star cannot be that massive. Nothing we know of can be that massive, that small, and that dark. Stephen Hawking bet against it. In 1974, he made a wager with the American physicist Kip Thorne that Cygnus Zone was not a black hole as an insurance policy, he explained, because he had spent his career working on black holes, and if they turned out not to exist, he would at least have the consolation of winning the bet. The stake was a subscription to a satirical magazine if he won, and a subscription to a men's magazine for Thorne if he lost. He conceded in 1990, broke into Thorne's office while Thorne was in Russia, and signed the concession. Thorne's wife was not pleased with the prize. At the center of our own galaxy sits something considerably larger. The center of the Milky Way is invisible to us. In ordinary light, there is too much dust in the plane of the disk between here and there, 26,000 light-years of it. But infrared light penetrates dust. And so, from the early 1990s onward, two teams, one led by Reinhard Genzel in Germany, one by Andrea Ghez in California, began photographing the central region in the infrared, year after year, using adaptive optics to cancel out the blurring of the atmosphere. They were tracking individual stars. Over 25 years, they watched a handful of stars trace out complete orbits around a point in space where there was nothing to see. One of them, a star designated Stu, completes an orbit in about 16 years, sweeping in to within 17 light hours of the center at closest approach, closer than Uranus comes to the Sun, and traveling, at that moment, at nearly 3% of the speed of light. From those orbits, by the same Newtonian arithmetic anyone can do with Kepler's laws, they weighed the object at the focus, 4.3 million times the mass of the Sun, and confined within a region smaller than the orbit of Mercury. There is no configuration of ordinary matter, no cluster of dead stars, no arrangement of anything we know about that can be that heavy and that compact and remain stable. Genzel and Ghez shared the Nobel Prize in 2020. The object is called Sagittarius A star, and it is at the center of the galaxy you are inside. In 2019, we finally looked at one directly. The Event Horizon Telescope is not a telescope. It is a set of radio dishes scattered across the planet, from Hawaii to Chile to the South Pole, whose signals are synchronized by atomic clocks and combined so that they behave, collectively, as a single instrument the size of the Earth. It has the angular resolution to read a newspaper in another city. They pointed it at the giant black hole at the center of the galaxy. Messier, 87, 55 million light-years away, a monster of 6.5 billion solar masses. The image that came back showed a ring of light with a dark hole in the middle, photons bent by gravity into orbit around the black hole, forming a bright ring around a shadow. The ring was brighter on one side, as relativity predicts it should be for a rotating hole whose material is coming toward us on that side. The size of the shadow matched the prediction from Schwarzschild's solution and its rotating successors. A century after a man in a trench wrote down a solution he did not believe in, we photographed the thing it described. And in 1974, Hawking had shown that the picture was not final. Applying quantum field theory to the region just outside the horizon, he found that a black hole is not perfectly black. It radiates, faintly, thermally, at a temperature inversely proportional to its mass, which means the giants radiate essentially nothing, and only a small hole would glow appreciably. A black hole of stellar mass has a temperature of billionths of a degree above absolute zero, far colder than the cosmic microwave background bathing it, so it absorbs more than it emits and grows rather than shrinks. But run the universe forward long enough, past the point where the background has cooled below even that, and the black holes begin to evaporate, slowly. The evaporation time for a stellar mass hole is longer than the current age of the universe, by a factor with 60 or so zeros in it. Hawking radiation has never been observed. It may never be observed. It is one of the very few places where quantum mechanics and gravity have been made to speak to each other, and what it implies is a problem nobody has solved. If a black hole evaporates completely, what happens to the information about everything that fell in? Quantum mechanics says information cannot be destroyed. The black hole appears to destroy it. 50 years on, this remains an open argument among serious people. And then, in September of 2015, at 5:51 in the morning, the two detectors of the Laser Interferometer Gravitational Wave Observatory registered a signal 7 milliseconds apart. It lasted about a fifth of a second. It rose in frequency and then stopped. It was two black holes, about 36 and 29 times the mass of the Sun, spiraling into each other and merging, 1.3 billion light-years away. The final black hole weighed about 62 solar masses. 3 solar masses were missing. Those 3 solar masses were converted, in a fraction of a second, into gravitational waves into a ripple in the geometry of space itself, radiating outward at the speed of light. For that fifth of a second, the power output of that collision exceeded the combined light of every star in the observable universe. By the time it reached Earth, after 1.33 billion years of travel, it stretched the 4-kilometer arms of the detector by about 1 part in 10 to the 21st, a distance 1,000 times smaller than a proton. We measured it. We have now measured it in a couple of hundred further events, and a separate technique, using the timing of pulsars scattered across the galaxy as a network of clocks, has begun to pick up the low background hum of supermassive black holes merging across cosmic history. The invisible turned out to be audible after all. But this whole story has been about gravity pulling things together. There is something in the universe doing the opposite, and it is winning. 8. The thing that pushes. The question the two teams set out to answer, in the early 1990s, was how fast the expansion of the universe is slowing down. Not whether, how fast. The universe has been expanding since the beginning, and it is full of matter, and matter attracts matter. so gravity must be applying a brake. Everyone agreed on this. The only question was whether the brake was strong enough to eventually stop the expansion and pull everything back into a final collapse, or whether the universe would coast outward forever, decelerating but never quite halting. To answer it, you need to measure distances to objects very far away and compare those distances with how fast the objects are receding. Nearby, the relationship is simple and linear. Far away, it should curve, and the direction and amount of the curvature tell you how the expansion rate has changed over cosmic time. The trouble is measuring the distances. The tool they used is a particular kind of exploding star. A Type 1, a supernova happens when a white dwarf, that cooling Earth-sized cinder held up by degeneracy pressure, sits in a binary system and pulls material from its companion. It grows, and as it grows, it approaches the Chandrasekhar limit, the 1.4 solar masses calculated on that steamship. Just before it gets there, the carbon in its interior ignites, all at once, throughout the entire star. There is no core, no shell, no gradual burning. The whole object detonates and is completely destroyed. The useful thing about this is that it always happens at the same mass. The trigger is a fixed number from quantum mechanics, and so the explosion has, near enough, a fixed intrinsic brightness. It is a standard candle, a light bulb whose true wattage you know. Compare its true brightness with how bright it looks from Earth, and you have its distance. Near enough is not exactly. Type 1, a supernovae do vary, by up to a factor of 2 or 3. What made the whole enterprise possible was a correction discovered by an astronomer named Mark Phillips in the early 1990s. The brighter ones fade more slowly. The shape of the light curve, how quickly the explosion dims over the weeks after peak, tells you how luminous it truly was. Calibrate with that, and the scatter collapses to a few percent. So 2 teams went hunting. One was the Supernova Cosmology Project, based at Berkeley and led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt in Australia, with a young postdoctoral researcher named Adam Ries doing much of the analysis. They were rivals, and the rivalry was not always friendly. The practical problem was brutal. A supernova is visible for a few weeks and then it is gone. Time on the world's largest telescopes is allocated months in advance, in a competitive process. You cannot apply for telescope time to observe a supernova that has not exploded yet. Perlmutter's team solved this with a scheduling trick. They would take wide-field images of the same patches of distant sky just after a new moon, then take the same images again just before the next new moon, and subtract one from the other. Anything that had appeared in between showed up as a new point of light on an otherwise blank subtracted frame. They could therefore guarantee, statistically, that they would deliver a batch of fresh supernovae on a known date, and so they could book the big telescopes in advance for the follow-up spectra before they had found anything at all. It worked because supernovae are, in aggregate, reliable, even though individually they are not. By the mid-90s, both teams were accumulating distant supernovae at redshifts implying that the light had been travelling for billions of years. And the numbers were wrong. The distant supernovae were too faint, not by much, about 25%, a quarter of a magnitude, but faint means far. And they were further away than they should have been for their redshift, which meant the universe had expanded more between then and now than a decelerating universe would allow. The deceleration was not merely small, it was negative. The expansion had been slowing for the first several billion years, while matter was dense and gravity had the upper hand, and then, roughly 5 or 6 billion years ago, it had crossed over and begun to accelerate. It is accelerating now, it is accelerating tonight. Both teams checked everything. Dust, which reddens and dims light, could produce a false faintness, but dust reddens, and the supernovae were not reddened. Evolution. Perhaps ancient supernovae are intrinsically dimmer than modern ones, being made from stars with fewer heavy elements. That was harder to exclude, and it took years of further work to exclude it. Selection effects, calibration errors, the lot, nothing removed the signal. They announced within weeks of each other. In early 1998, Ries was 28. Perlmutter, Schmidt, and Ries shared the Nobel Prize in 2011. The universe contains something that pushes. The simplest description of it is a term that Einstein had already written down and then deleted. 80 years earlier. In 1917, when everyone including Einstein believed the universe was static and eternal, he noticed that his own equations would not permit a static universe. A universe full of matter must collapse under its own gravity. So he added a term, a constant, denoted by the Greek letter lambda, an energy intrinsic to empty space itself, which would push outward and exactly balance the inward pull. It was a fudge, and it did not even work. The balance is unstable, like a pencil on its point. When Hubble showed in 1929 that the universe was expanding, the need for it vanished, and Einstein dropped it. George Gamow later reported that Einstein had called it his biggest blunder, though the phrase appears nowhere in Einstein's own writing, and Gamow was not always a careful witness. Lambda came back in 1998, and it fits. Every measurement made since, and there have been many, using entirely different techniques, is consistent with dark energy being a constant energy density of empty space, unchanging as the universe expands, which is a very strange thing for it to be. As space expands, the matter in it thins out. A constant energy density of space itself does not thin out. There is simply more space, and therefore more of it, which is why it has come to dominate. It did not grow stronger. The universe grew emptier, and the competition went away. Then comes the number that ought to worry anyone who looks at it. Quantum field theory says empty space is not empty. The vacuum seethes with fluctuating fields, with virtual particles appearing and vanishing, and all of that activity should carry energy, precisely the kind of energy that would behave like a cosmological constant. So physicists calculated what the vacuum energy of empty space ought to be. The answer is larger than the observed value of dark energy by a factor of about 10 to the power of 120. Not 120%, a 1 followed by 120 zeros. That is not a discrepancy that can be tidied up. It is the largest disagreement between theory and observation in the history of physics. Something is fundamentally broken in our understanding of the vacuum, and nobody has any idea what. The most common response is to assume that some unknown mechanism cancels the vacuum energy almost exactly to 120 decimal places and leaves behind the tiny residue we observe. Nobody can name the mechanism. The alternative is that dark energy is not a constant at all, that it is a field, evolving slowly over cosmic time, sometimes called quintessence. If so, its strength would change, and the expansion history would deviate slightly from the constant lambda prediction. The European Space Agency's Euclid telescope, launched in 2023, is mapping billions of galaxies specifically to test this. A very large ground-based survey has recently produced hints not yet conclusive, and contested that dark energy may have been slightly stronger in the past than it is now. If that holds up, lambda is wrong, and something considerably more interesting is going on. If it does not, we are left with a constant we cannot explain by a factor of 10 to the 120th. Follow the acceleration forward and the future it produces is quiet. The galaxies of our local group, the Milky Way, Andromeda, and a few dozen small companions are bound to each other by gravity, and gravity is winning locally. They will remain. In a few billion years, Andromeda will collide with the Milky Way, and the two will merge into a single large elliptical galaxy. Everything else will leave. As the expansion accelerates, more and more distant galaxies will cross beyond the cosmic horizon. The boundary past which the space between us and them is expanding faster than light can cross it. Their light will stretch, redden, dim, and cease to arrive. Not because they have gone anywhere, because the space between has grown too fast for anything to bridge it. Given enough time, 100 billion years, a trillion an observer in that merged galaxy will look out at the sky and see nothing beyond their own island of stars. The cosmic microwave background will have redshifted into undetectability. The evidence for the expansion will be gone. The evidence for the Big Bang will be gone. The evidence for dark energy, the very thing that removed the evidence, will be gone with it. An astronomer in that era, with perfect instruments and complete honesty, would conclude that they lived in a single galaxy, in a static, empty, eternal universe, and they would be wrong, and there would be no possible observation available to them that could show it. We are living in the window when the information is still here. It will not always be. The light from the distant universe is arriving tonight, and there was a time before it could arrive, and there will be a time after. That light includes the oldest light of all, which is not out there at the edge of things. It is in this room, and it is the reason we know how much dark matter there is, to 3 decimal places, without ever looking at a single galaxy. 9. The oldest light, and the weighing of the dark. In 1964, 2 radio astronomers at Bell Laboratories in New Jersey were trying to get rid of a noise. Arno Penzias and Robert Wilson had inherited a horn antenna. A large, oddly shaped metal structure originally built to catch signals bounced off early communications satellites. They wanted to use it for radio astronomy, and radio astronomy requires that you understand every source of noise in your system before you can trust a signal. So they set about accounting for all of it. There was a hiss they could not account for. It was faint, corresponding to a temperature of a few degrees above absolute zero, and it would not go away. It did not come from New York City, which they checked by pointing the antenna at it. It did not vary with the time of day, which ruled out the sun. It did not vary with the seasons, which ruled out anything in the solar system. It did not concentrate along the plane of the Milky Way, which ruled out our own galaxy. It came from every direction in the sky, in equal measure, which is not how any known source behaves. They cooled their receiver with liquid helium. They rebuilt the electronics. They taped over the joints in the antenna. They found a pair of pigeons nesting in the horn, and they evicted them. And they cleaned out what Penzias later described in print as a white dielectric substance, which is a phrase worth admiring. The pigeons came back. They were dealt with more permanently, a fact that Penzias mentioned afterwards with visible discomfort. The hiss remained. 30 miles away, at Princeton, a group led by Robert Dicke was building an antenna specifically designed to look for exactly this signal. Dicke had reasoned that if the universe began in a hot, dense state, the radiation from that era must still be here, cooled by the expansion of space to a few degrees above absolute zero, filling everything, coming from all directions. He was not the first to think of it. George Gamow, Ralph Alpher, and Robert Herman had predicted the existence and roughly the temperature of this radiation in the late 1940s, and their prediction had been ignored, forgotten, and by Dicke's group, who had not read it independently rediscovered. A colleague made the connection between the two groups and Penzias telephoned Dicke. Dicke listened, hung up, turned to his team, and said, "Boys, we have been scooped." The two groups published side by side. Penzias and Wilson described a measurement they had not been trying to make and did not initially understand. Dicke and his colleagues explained what it was. Penzias and Wilson received the Nobel Prize in 1978. What they had found is the cosmic microwave background, and here is what it is. Go back to when the universe was about 380,000 years old. It is uniformly hot, a few thousand degrees, and it is a plasma. The electrons have not yet been captured by the nuclei. They are free, and free electrons scatter light ferociously. A photon in that environment travels no distance at all before being knocked sideways. The universe is opaque. It is glowing, everywhere, at every point, and none of the light can get anywhere. It is like being inside the sun. Then the expansion cools it below about 3,000 degrees, and in a relatively short interval the electrons combine with the protons to form neutral hydrogen atoms. Neutral hydrogen does not scatter light the way free electrons do. The fog lifts. Every photon that was bouncing around suddenly finds itself able to travel in a straight line, in whatever direction it happened to be going at that moment. Most of them have been travelling ever since. 13.8 billion years, uninterrupted. The expansion of space has stretched their wavelengths by a factor of about 1100 as they travelled, dragging them from the visible and infrared down into the microwave, and cooling the radiation from 3,000 degrees to 2.725 degrees above absolute zero. There are about 400 of these photons in every cubic centimetre of space. In the volume of your bedroom, there are more photons from the early universe than there are stars in the observable cosmos. They are passing through you, along with everything else, and they have been travelling since before there were atoms. If you are old enough to remember an analog television tuned to a dead channel, a small fraction of that static, around 1% of it, was this: the oldest light in existence, arriving in a living room and being mistaken for nothing. For nearly 30 years the background looked perfectly smooth. Then, in 1992, the Cosmic Background Explorer satellite reported two things. The first was that the spectrum of the radiation is a perfect thermal curve, the exact shape a body in thermal equilibrium at 2.725 degrees should produce. The measurement was so precise, and the agreement so exact that when the plot was shown at a meeting of the American Astronomical Society, the room stood and applauded a graph. It is the most perfect blackbody spectrum ever measured, anywhere, by anyone, including in a laboratory. That is what the early universe was. A body in equilibrium, everywhere, at once. The second finding was that the temperature is not quite the same in all directions. There are variations, hotter patches, colder patches, at a level of about 1 part in 100,000. Those variations are everything. They are the seeds. Slightly denser regions in the early universe were slightly cooler in a specific way, and being denser, they pulled in more material, and grew, and eventually became galaxies and clusters and superclusters and the great filaments of the cosmic web. The colder, emptier regions became the voids. The entire architecture of the universe, every structure that has ever existed, including this one, is written in that map as a pattern of faint blotches. The subsequent satellites, the Wilkinson Microwave Anisotropy Probe, and then Planck, mapped those variations to extraordinary precision. And here the story comes back to where it began, because those maps are how we weigh the dark matter. The mechanism is worth understanding, because it is the strongest single piece of evidence in the whole field, and it does not involve looking at a galaxy at all. Before the fog lifted, the universe was a plasma, and a plasma, like any fluid, can carry sound waves. And it did. The tiny initial density fluctuations acted as starting points, and pressure waves propagated outward from them through the hot plasma, compressing and rarefying it for 380,000 years, until the moment the plasma turned into neutral gas and the sound stopped. The universe rang, and then it went silent, and the light that escaped at that instant carries a snapshot of the ringing. When you analyze the temperature map statistically, asking how much variation there is on each angular scale, you get a series of peaks. These are the harmonics of that primordial sound, the fundamental and its overtones, waves that had just reached maximum compression at the moment the fog lifted, waves that had compressed and rebounded once, and so on. Now here is the crucial part. Ordinary matter participates in the sound. It is charged, it is coupled to the photons, it feels the pressure, it oscillates. Dark matter does not. Dark matter does not interact with light, so it feels no radiation pressure at all. It just sits in its gravitational wells and pulls, indifferent to the ringing going on around it. That difference leaves a fingerprint. The gravity of the dark matter deepens the compressions and does nothing for the rarefactions, which makes the odd-numbered peaks in the pattern taller than the even-numbered ones by an amount that depends directly on how much dark matter there is relative to ordinary matter. So you measure the height of the third peak, and from that you read off, with real precision, the amount of a substance that has never been detected in any laboratory on Earth. The answer is that dark matter outweighs ordinary matter by a factor of about 5 to 1, which is the same answer that comes from galaxy rotation curves, and the same answer that comes from galaxy clusters, and the same answer that comes from gravitational lensing, and the same answer that comes independently from the deuterium abundance left over from the first 20 minutes. 5 completely different methods, drawing on completely different physics, measuring completely different things, arriving at the same number. That is why the community believes in something it has never touched. Not because of any one measurement, because the measurements have no business agreeing, and they agree. The same maps deliver the rest of the inventory. The universe is 13.8 billion years old to within about 20 million years. It is spatially flat to within a fraction of a percent. It is 5% ordinary matter, 27% dark matter, 68% dark energy, and the maps contain a problem that has never been solved. The background is too uniform. Look at 2 patches of sky in opposite directions. The light from each has been travelling for the whole age of the universe, which means they are separated by more than twice that they are, and always have been, too far apart for any signal, even light, to have passed between them. They have never been in contact. They have no shared history. Nothing that happened in one could ever have influenced the other. And they are at the same temperature, to 1 part in 100,000. That should not be possible. Things reach the same temperature by exchanging heat, and these regions have never been able to exchange anything. This is the horizon problem, and it is a genuine hole in the Big Bang model as originally written. In 1980, a postdoctoral researcher named Alan Guth proposed a fix that is either the most audacious idea in cosmology or a very sophisticated way of hiding our ignorance? And the honest answer is that the field has not fully decided. Inflation. In the first fraction of a second, perhaps 10 to the minus 36 seconds after the beginning, the universe underwent a brief, violent, exponential expansion, driven by the energy of some field, and grew by a factor of at least 10 to the 26 in a time so short that the word instant is generous. A region far smaller than a proton was inflated to a size larger than everything we can now see. If that happened, the horizon problem dissolves. The opposite sides of the sky are at the same temperature because they were in contact, they were adjacent, in causal contact, in thermal equilibrium, before inflation blew them apart. It also explains why the universe is so precisely flat, and it gives you the initial density fluctuations for free. Quantum fluctuations in the inflating field, stretched from subatomic to cosmic scale, frozen in, and eventually becoming the blotches on the map, which became the galaxies, which became this. Inflation is not proven. It fits, and it fits well, and it has no serious rival, and it remains unconfirmed. The decisive test would be primordial gravitational waves, ripples in space-time generated by inflation itself, which would leave a very specific twisting pattern in the polarization of the background light, a pattern that nothing else can produce. In March of 2014, a collaboration operating a telescope at the South Pole announced that they had found it. There was a press conference. Guth was filmed being told the news at his front door. Within months it fell apart. The signal was real, but it was not from the early universe. It was dust-polarized emission from magnetically aligned grains of dust in our own galaxy. Foreground contamination that had been underestimated. The claim was withdrawn. The search continues. There are telescopes at the South Pole doing it right now, tonight, while you are lying there. And the light they are looking at is the same light that is in your room. It is not distant. It has arrived. It is passing through the walls and through the bed and through you at this moment, along with the dark matter, along with the neutrinos, along with everything else that does not stop. 10. What it might be. Before there were galaxies, there was a nearly uniform gas and a nearly uniform sea of something else, and the something else went first. Run the sequence in order. Emerging from the era of the background light, the ordinary matter is hot, and it has just stopped being a plasma, and it is spread out very smoothly indeed. The density variations, remember, are 1 part in 100,000. Gravity would like to gather it. Left alone, it would take an enormous span of time to do so, because gravitational collapse from such tiny seeds is slow, and until recently the gas had radiation pressure fighting it every step of the way. The arithmetic does not work. Starting from that smoothness, with only ordinary matter, and with only 13.8 billion years available, you cannot make galaxies. There is not enough time. The universe would still be a warm fog, but the dark matter never had radiation pressure fighting it, because it never touched the radiation. It was free to start collapsing while the ordinary matter was still trapped in the plasma, still ringing with sound waves, still going nowhere. By the time the fog lifted, the dark matter had a substantial head start. It had already built a network of gravitational wells, and the ordinary gas, suddenly released, fell into them. The scaffolding came first. Everything else was infill. This is not a story anyone told for its elegance. It is what emerged when people put the physics into a computer and let it run. The simulations are among the most impressive things in computational science. You begin with a box of virtual universe, seeded with the density fluctuations that the background radiation actually shows us not invented, measured. You fill it with particles representing dark matter. You apply gravity. You press start, and you let 13.8 billion years of expansion and collapse play out. What forms is not a random scatter of blobs. It is a structure. The matter drains out of the low-density regions, leaving enormous voids, hundreds of millions of light years across, nearly empty. It collects into sheets. The sheets drain into filaments, long, thin, dense threads of dark matter. And where filaments intersect, at the nodes, the material piles up into the great halos where galaxy clusters form. The result looks like a web. Astronomers call it the cosmic web, and there is nothing metaphorical about the name. It is a network of filaments and nodes and voids. and it is the largest structure in existence. The test of the simulation is whether the web it produces looks like the real one, and we can check, because over the last 30 years, survey telescopes have measured the redshifts of millions of galaxies and built three-dimensional maps of where they actually are. The maps show voids, they show sheets, they show filaments, with galaxies strung along them like beads and clusters at the intersections. The statistics match, not qualitatively, quantitatively. The distribution of structure, on every scale from a few million light-years up to the largest measurable, comes out of the simulations and out of the sky in agreement. And the simulation only works if you put dark matter in it. Take it out, and the web does not form. There is one more independent measurement hiding in the survey maps, and it is my favourite piece of evidence in the whole subject, because it connects two things that have no obvious reason to be connected. Remember the sound waves in the primordial plasma? They travelled outward from every density peak at a substantial fraction of the speed of light for 380,000 years, and then they stopped. Abruptly, when the plasma became neutral gas. The ordinary matter carried outward by each wave was left stranded at the radius the wave had reached at the moment the music stopped, and the dark matter, which never rode the wave, stayed in the middle. So around every original density peak, there is a shell of slightly enhanced ordinary matter at one particular distance and a concentration in the centre. The distance is fixed by physics, the speed of sound in the early universe, multiplied by the time available. It works out to about 500 million light-years in today's stretched-out coordinates, which means galaxies today should be very slightly more likely to be found 500 million light-years apart than at any other separation, not a strong preference. A faint excess of about 1%, a whisper of structure, laid down when the universe was a plasma, and detectable now as a statistical bump in a catalogue of galaxy positions. It is there. It was found in 2005 in 2 independent surveys, and it has since been measured with high precision. A frozen sound wave from the first 400,000 years imprinted on a map of galaxies at exactly the size the theory predicts. It is now used as a cosmic ruler, a known length, at many different distances, which allows the expansion history of the universe to be measured directly. So, the web is right, the ruler is right, the sound waves are right, the peaks are right, the deuterium is right, the lensing is right, the rotation curves are right. Every large-scale test passes. And yet, on small scales, the picture has cracks. They have been there for 25 years, they have not gone away, and honest people in the field argue about them. The first is called the core cusp problem. The simulations, run with collisionless cold dark matter, consistently predict that the density of a halo should rise steeply toward the centre, a sharp spike, a cusp. When astronomers measure the actual dark matter distribution in the centres of small galaxies, particularly the dim, slowly rotating dwarf galaxies where the measurement is cleanest, they often find something flatter. A core, not a cusp. Something has smoothed out the middle. The second is the missing satellites problem. Simulations predict that the Milky Way's halo should be swarming with hundreds or thousands of small subhalos, miniature clumps of dark matter, each of which ought to have collected a little gas and lit up as a dwarf galaxy. For a long time we knew of a couple of dozen, not hundreds. The third is called, with a certain bleakness, too big to fail. The largest of the predicted subhalos are so massive that they really should have formed visible stars. They are too big to have quietly failed to become galaxies, and we do not see them. These are real discrepancies, and for a while they were the strongest argument that something was wrong with the theory. But they may be dissolving, and the reason is not dark matter at all. It is that the simulations, for a long time, contained only gravity, and real galaxies contained supernovae. When stars form in a small galaxy and then explode, they drive powerful winds of gas outward. Gas has mass. Move enough of it, violently and repeatedly, and the gravitational potential of the whole galaxy sloshes, and that sloshing can transfer energy to the dark matter and flatten a cusp into a core. Simulations that include this feedback do produce cores, and the same violence can strip the gas out of the smallest halos entirely before they can form stars, leaving them dark and invisible, which would explain the missing satellites, not as missing halos, but as halos with no light in them. The prediction from that argument is that there ought to be a great many very faint dwarf galaxies around the Milky Way that we simply have not spotted, and over the last 15 years, deeper surveys have found them. Dozens of them, extremely faint, some containing only a few hundred stars, all of them heavily dominated by dark matter, some with mass-to-light ratios in the hundreds, TOE, meaning they are almost entirely dark objects with a sprinkling of stars on top. The count keeps rising, the discrepancy keeps shrinking. It has not vanished. And then there is the object that nobody expected, which is a galaxy with no dark matter in it at all. In 2018, a team measuring a faint, diffuse galaxy in the constellation Cetus found that its globular clusters were moving very slowly, so slowly that the mass required to hold them in orbit was no more than the mass of the visible stars. No halo, no missing mass. A galaxy that appears to obey Newton's laws exactly, with nothing invisible added. The measurement has been argued over ferociously, mostly about the distance to the galaxy, which affects everything. But if it holds, and a second, similar galaxy has been found nearby, which makes a fluke less likely then, it is a strange and rather beautiful piece of evidence, and it points in an unexpected direction. Because if you believe in modified gravity, a galaxy without dark matter is a disaster. You cannot switch the law of gravity off in one particular galaxy. If the law says that low accelerations produce extra pull, it says so everywhere, in every galaxy, always. A galaxy whose stars move exactly as Newton predicts is a galaxy where the modification did not happen, and there is no way to arrange that. Whereas if dark matter is a substance, a galaxy can lose it. It can be stripped away in a collision, or torn off by tidal forces during an encounter with a larger galaxy, leaving the stars behind. Substances can be removed. Laws of nature cannot. The galaxy with nothing in it turns out to be an argument that the something is real. So what is it? The honest answer is that there are 4 families of candidate and no evidence for any of them. The first is the WIMP, the weakly interacting massive particle. A heavy particle, perhaps 100 times the mass of a proton, interacting through gravity and through the weak nuclear force and nothing else. Its appeal was arithmetical and rather lovely. If you assume such a particle existed in the hot early universe and simply calculate how many of them would have survived as the universe cooled and expanded, you get, without tuning anything, roughly the observed density of dark matter. The coincidence was so neat it acquired a name, the WIMP miracle, and it drove 30 years of experiments. The xenon tanks were built to find it. The Large Hadron Collider was expected to produce it. Neither has. The parameter space where the miracle lives has been largely excluded. The WIMP is not dead, but it is much quieter than it was. The second is the axion, a very light particle, proposed for entirely unrelated reasons to solve a technical puzzle in the theory of the strong nuclear force. Nobody was trying to explain dark matter when the axion was invented. It turned out, afterwards, that if axions exist, they would have been produced in the early universe in vast numbers and would behave, on large scales, exactly like cold dark matter. A particle proposed to fix one problem, which happens to fix a completely different one, is the kind of thing physicists find persuasive. The microwave cavity experiments are hunting it. They have searched a small slice of the possible masses. The third is the sterile neutrino, a heavier cousin of the ordinary neutrino that does not even feel the weak force, and interacts only through gravity, making it invisible even by the standards of a particle already famous for being difficult to catch. The fourth is that dark matter is black holes after all, not the stellar mass ones ruled out by the microlensing surveys, but primordial black holes, formed in the first fraction of a second from density fluctuations rather than from collapsing stars, in a range of masses where the observational constraints are still weak. It is a minority view, it is not excluded. And beneath all 4 there is a 5th possibility that nobody can rule out, which is that dark matter is not one thing. Ordinary matter is not one thing. It is protons and neutrons and electrons and neutrinos and photons and a whole zoo of unstable particles interacting through 3 separate forces of varying strength. There is no principle requiring the other 85% to be simpler than the 15. There could be a dark sector, several species of dark particle, with their own forces, their own interactions, their own physics, entirely invisible to us because none of it couples to light. If that is true, then the universe contains an entire second kind of matter with its own internal structure, sitting in the same rooms as ours, passing through it, having its own complicated history, and touching us only through gravity. We would have no way of knowing. The landing. We began in this room, and it is where we finish. The dark matter is still passing through you. It has not stopped for any of this. It did not stop while we were with Zwicky at Mount Wilson, or with Rubin at the eyepiece watching a curve refuse to fall, or with Chandrasekhar on a steamship in 1930, or with two men in New Jersey evicting pigeons from an antenna that was picking up the beginning of the universe. It has been moving through the walls of every room you have ever slept in, at hundreds of kilometers per second, arriving out of the direction of Cygnus, since before you were born. It went first. That is perhaps the thing worth carrying. Before there was a Milky Way, there was a well in the dark that the Milky Way would fall into. Before there was a sun, there was a halo. The scaffolding was raised by something that has never emitted a photon, and the gas came afterwards, and fell in, and cooled, and formed stars, and the stars made the carbon and the oxygen and the calcium and the iron, and some of that material ended up in a cold cloud, and some of that cloud collapsed into a star with planets, and on one of those planets the carbon and the oxygen and the calcium and the iron have been arranged, temporarily, into a person who is lying in the dark listening to this. You exist downstream of it, all of it, and the thing at the top of that sequence, the thing that made the wells, that made everything else possible, is a substance we cannot name. Here is the state of the search, honestly. 90 years since Zwicky wrote it down in German, in a Swiss journal that nobody read. 50 years since Rubin's curves made it unavoidable. 40 years of detectors buried under mountains and in gold mines and beneath lakes, tanks of liquid xenon cooled to 100 degrees below zero, waiting for a single atomic nucleus to be knocked sideways. Microwave cavities in a magnet, tuned like a radio, scanning frequency by frequency. Colliders driving protons into each other at energies not seen since the first fraction of a second, looking for something to be missing from the wreckage. Nothing. In all of it, nothing. That is not a failure. A null result is a measurement. Every year of silence rules out possibilities, closes doors, narrows the space in which the answer can be hiding. We know a great deal about what dark matter is not. It is not ordinary matter that failed to shine the deuterium left over from the first 20 minutes forbids it. It is not dead stars or rogue planets the microlensing surveys looked, and there were not enough. It is not a mistake in our arithmetic 5 independent methods, using unrelated physics, agree on the number. It is probably not a modification of gravity the bullet cluster separated the mass from the matter, and one small galaxy in Cetus appears to have none of it at all, which no law of nature could arrange. What we are left with is a substance, present in every galaxy, mapped in 3 dimensions across the observable universe, weighed to within a few percent, entirely unidentified. And so the honest inventory, tonight, reads like this. We know how much there is, we know where it is. We know what it did. It built the wells that everything fell into. We know it was already gravitationally dominant 380,000 years after the beginning, because the third peak in the ancient light says so. We know it does not touch light, and does not touch itself, and barely touches us. We do not know what it is made of. We do not know how many kinds of it there are. We do not know whether it will ever be caught in a tank, under a mountain, or whether the whole idea of catching it, of building a machine that a thing can walk into, is the wrong picture entirely. The boundary between what we know and what we do not is not out there, at the edge of the observable universe, or behind the horizon of a black hole where the equations give up. It is not somewhere far away that you would need a spacecraft to reach. It is in the room. It is in the bed. It is in the small space between your closed eyes and the inside of your skull. Billions of particles a second, arriving out of Cygnus, crossing the walls, crossing your body, crossing the floor and the earth beneath it, and out into space on the other side of the world, having noticed nothing, having left nothing, having been here. They will still be there in the morning, they will be there tomorrow night and the night after, and they were there every night of your life before you ever heard about them. We have no idea what they are. Good night.